Think about the logistical problem of representing reality on a single piece of paper. You have to figure out how to fit a massive suspension bridge onto the exact same size page as a microscopic organism. Engineers, architects, and scientists solve this size difference using a single mathematical tool, the scale of drawing. The concept relies on a strict formula. The scale of drawing equals the length in the drawing divided by the real length. Working with this formula comes with two strict rules. First, a final scale is a pure mathematical ratio. It has 0 units attached to it. Measurements like centimeters and meters are deleted from the final answer. Second, to make that first rule mathematically possible, both lengths in your formula must be converted into the exact same unit before you divide them. By matching the units and dividing, you create a unitless multiplier that bridges the gap between your page and reality. Let's test this on a standard map. We need to find the specific scale if the real distance between two cities is 300 kilometers, but they are only 6 centimeters apart on the drawing. Extracting data, 6 centimeters drawing length and 300 kilometers real length creates a unit mismatch. Since a kilometer is 100,000 centimeters, multiplying 300 by 100,000 gives 30 million centimeters. Dividing the 6 centimeter drawing by the 30 million real length simplifies to a 1 to 5 million scale. Whenever the first number in your ratio is a 1, making the overall value less than 1, you are dealing with minimization. You are actively shrinking reality to fit the page. We can also run this formula in reverse. Suppose an architect builds a model at a 1 to 500 scale. If the real skyscraper is 250 meters tall, what is the height of the model in centimeters? We set up our equation, 1 over 500 equals x over 250 meters. Pausing for a unit check, we multiply 250 by 100 to get 25,000 centimeters. Cross-multiplying 1 times 25,000 divided by 500 isolates x, revealing the model is 50 centimeters tall. Whether you are drawing cartographic maps or building architectural models, minimization relies on these exact same cross-multiplication mechanics. Let's flip the scenario entirely to the microscopic level. A 3 millimeter insect is blown up to 15 centimeters in a photograph. Pause the video and calculate the scale yourself. Let's check the steps. First, convert 15 centimeters into 150 millimeters. Then, divide the 150 millimeter drawing length by the 3 millimeter real length, leaving a ratio of 50 to 1. Because the first number in the ratio is larger than the second, the image scales reality up. This is explicitly called magnification. Let's pull everything together into a practical calculation. This is a room blueprint where every 1 centimeter on the paper represents 1.2 meters in reality. Based on the drawing's dimensions, we need to find the room's real total area. Starting with the length, we take the 3 centimeter dimension from the drawing and multiply it by our 1.2 meter scale factor. This gives us a real length of 3.6 meters. Next, we calculate the real width. We multiply the 2.5 centimeter dimension from the page by the 1.2 meter scale factor, resulting in a real width of 3.0 meters. Finally, to find the true area, we multiply our newly found real length by our real width. 3.6 meters times 3.0 meters reveals an actual room area of 10.8 square meters. To master scale of drawing, keep this summary in mind. Memorize the division formula, always convert your units first, and remember that ratios below 1 minimize, while ratios above 1 magnify. You can scan the QR code to take the quiz and test your skills.